All right, so we're going to do a quick review here of the Sagnac effect and relativity theory. What does relativity theory predict versus what's measured? So in relativity theory, Einstein states here at the beginning that all inertial frames are equally valid, and this is called the principle of relativity. So anywhere where the laws of mechanics hold good, so will his equations. And an inertial reference frame is being defined as a frame that's in uniform motion in a straight line. The next postulate is that the speed of light in these frames, in these inertial frames, as defined by the first posti, will measure the speed of light to be the same. It'll be constant, irrespective of the motion of the source or the observer. So when you use the reference frames to analyze the first postulate, the observers in those reference frames will measure the speed of light being the same, and they will not be able to use a timing difference due to a distance change to determine any sort of velocity between them. Secondly, at the bottom here, he says an introduction of a luminiferous ether will prove superfluous inasmuch as the theory developed here will not require an absolutely stationary space provided with special properties, nor assign a velocity vector to a point of empty space in which electromagnetic processes took place. So what he's saying there is we don't need a physical medium to put a cap on the speed of light. And we also don't need a mathematical frame coordinate system that we use to measure absolute velocity against, because all motion will be relative. And in my theory, time and space will be functions of the square of velocity over c squared, and that will make all time and space relative to some other coordinate system based on velocity. It'll change, in those coordinate systems, when you analyze them, it'll change based on the velocity that you're doing the analyzation with. So when we get into the Sagnac effect with the rotating interferometer, but before we do that real quick, Einstein needs to tell us where his equations also apply, and that is in a uniformly rotating system here. So we're going to go over that real quick. Polygon. So here, he's saying that his equations also hold true in any polygonal line where points A and B coincide. And we will assume that the results proved for any polygonal line is also valid for a continuously curved line, otherwise known as a circle. So any circle that's moved in a constant velocity or any closed polygonal line will be in accordance with his equations. You can apply them there. So when you apply his equations to a rotating interferometer, where you would have the observer, which would be the photographic recorder, and you would have the light source, which is the laser emitter or the light emitter, whatever that you're using. On the rotating platform, that would be considered an inertial frame, and relativity predicts for observers in inertial frames that the speed of light is measured at a constant. Yet this apparatus produces a measurement where the phase difference in light is directly proportional to how fast the apparatus was rotating. And in a linear variant in 2004, it was shown that you can also do this in a straight line configuration, moving in a straight line. So that's a separate issue here, but we're looking at just the classical rotating reference frame situation, though, for this analysis. So what we have is, let's see, we got Einstein telling us where his equations apply, and then we get into what the classic theory predicts for the fringe displacement for a rotating interferometer versus what relativity predicts. Now, for the classic theory, for going clockwise and counterclockwise, accounting for the timing difference with respect to the distance change, if you use absolute space to preserve the distance so that you can account for the full length, that, as if the mirror is like rotating out from underneath the light, so to speak, so it has to catch up, or it rotates into it so it gets there faster. If you account for that, you correctly predict the fringe displacement based on the path length light has to travel and based on the rotational speed over the speed of light in the wavelength you're using, essentially. And that will predict how much the timing difference will be with respect to the clockwise and counterclockwise rotations. When you try to predict the displacement using relativity theory and you follow Einstein's postulates that you will not assign imaginary vectors or anything like that, then you do not correctly predict the fringe displacement. What you predict is that the speed of light will complete the circuit on clockwise and counterclockwise at the same time, irrespective of any distance change or timing change, or which will lead to no timing change, which predicts zero fringe. So you can't do this unless you do something like our boy Millikan does, specifically where you violate Lorentz symmetry. What does a violation of Lorentz symmetry look like? Well, Lorentz symmetry, as noted by Einstein, is facilitated by, scrolled down a little too far, is facilitated by the change in the time axis and the distance axis, otherwise known as length contraction and time dilation. So if you do a transformation from one reference frame to another, you need to change these axes, both of these axes. Otherwise, you're not following Lorentz symmetry and you're violating mathematical covariance, which means that your mathematical usage is not physically meaningful. It's not providing a physically meaningful explanation to what you're asserting mathematically. And another thing that is to be noted here is that you have to show reciprocity between the frames. In other words, you can't have both frames agree on a distance or a time in one transformation. You have to be able to show that both of these values change under the transformation to maintain Lorentz symmetry. So what this guy proposes, this Millikan guy, to erroneously attribute the Sagnac effect as a relativistic effect, is he violates relativity's postulates mathematically and physically, right? So he breaks covariance by using an asymmetrical analysis, only accounting for the distance change. And by using absolute space to account for the distance change, he's then able to derive the timing difference. And that is not a valid use of the mathematical framework. That's not how you derive things in that theory, because that's violating space-time symmetry, which is violating the whole covariance usage of it. So when you get into the derivation here, this is a first order timing difference, from the classical equation. This is not in accordance with a Lorentz transformation. A Lorentz transformation would be changing both the time and distance as a function of velocity, which would predict zero fringe. So in an inertial frame, C would be measured as zero, or no fringe. It would be measured at a constant, so it wouldn't produce the fringe. All right, I think that pretty much covers everything. So there's no valid Lorentz transformation to explain the Sagnac effect as a relativistic effect. It cannot be done without violating Lorentz symmetry. And this is why it is a first order falsification of the theory, because just the rotating platform alone is, sufficient enough to take out the special theory as defined by Einstein. But, he did introduce the general theory, and people will say, well, rotation falls under the general theory, so we got to do that. And it's like, okay, well, we could take a look at Dufour and Pune, where they measured in an inertial frame. They measured the first order timing difference of a rotating platform, where the photographic recorder and the light source were fixed to the lab wall, and they were shooting beams at 45-degree angled mirrors at a rotating platform, and measured the first order timing difference. So that's That's impossible on relativity theory. It should predict no fringe displacement. It should predict that the speed of light completes the circuit irrespective of the distance change at the same time, producing no fringe, but yet a fringe is measured. And when you use the general theory to make the predictions, it still can't make the predictions unless you use that preferred frame. Otherwise, it's off by a factor of 10. That's the Forum Pune 1942. And then you can also get into the linear variant, which is Ruyong Wong, who measured the speed of light being different going in a linear motion. And that is a direct refutation to what relativity theory predicts, unless you violate these postulates about using absolute space in a medium to account for that. All right. That is the end of the video. Any thoughts, Galatrax?
I wasn't paying attention.
Nice.